All right, so today we're going to discuss reactions of carboxylic acids and then reactions of esters. And a reminder that tomorrow at 7 we're going to have our Zoom online question and answer session to prepare for exam number 2. Late this afternoon we're going to be filming the review, the part where we do the outline of topics, and so that will be posted by this evening on Learning Suite. So be sure to take a look at that and make note of any questions you have on those topics and come prepared to ask questions at our Zoom question and answer session. Okay? So as we start out discussing reactions of carboxylic acids, we're going to begin with the reaction that they don't undergo. You cannot mix a carboxylic acid and an amine and expect to form an amide because you have an acid-base reaction that occurs instead. Your amine, such as ammonia or any other amine, is going to be basic enough to deprotonate a carboxylic acid, generating this ammonium carboxylate salt. We know that acid-base equilibria are favorable if we convert stronger acids into weaker acids. An ammonium ion is a significantly weaker acid than a carboxylic acid. pKa of a carboxylic acid, usually between 4 and 5. pKa of an ammonium ion, usually around 9. Okay, so you see that we would have an equilibrium constant of about 10 to the 5th for this process. Okay, so we're not going to get an amide. Now, if we look here on the screen, this is a figure from the book. It says that you can mix a carboxylic acid and ammonia and heat it up and generate an amide. While technically this can happen, in practice it's not very practical. You're going to have to heat that up to about 200 degrees or so. If you form these salts and you heat these salts hot enough, you can drive water out, the elements of water out of those salts and cause them to collapse to form amides. But as I mentioned, that usually requires about 200 degrees of heat and is not practical at all. Okay, so at room temperature, at practical temperatures, you're not going to be able to make amides. So they really shouldn't be showing you this reaction. You'd be tempted to use it on an exam. It's not going to work. Okay, it doesn't work in the lab, doesn't work on exams. So we have other ways of making amides, and the acidic proton of a carboxylic acid interferes in all of the reactions we would try to perform to convert amides into carboxylic acid derivatives. So we need special reaction conditions or special reagents to convert our carboxylic acids into acid, chlorides, anhydrides, esters, and amides. The good news is we do have reagents and reaction conditions that work in all cases. Okay. Before we start with the acid chloride, let's address the anhydride one. This is another one that's misleading. It's true that if you heat up a dicarboxylic acid, you can drive off water, boil off water, and you end up with an anhydride. That only works for making 5- and 6-membered cyclic anhydrides. Any other anhydride, you're going to want to use the method that we learned yesterday. What method did we learn yesterday for making anhydrides? Think back 24 hours. There were 2 species that we could react together to make anhydride. Yes, Sydney? Yes, an acid chloride and a carboxylate, exactly. So what we would do is we would take a carboxylic acid and we would deprotonate it, make a carboxylate, and then react that with an acid chloride. So that's the best way of making anhydrides, not this. Okay? So technically we can make anhydrides from carboxylic acids. We just have to deprotonate first and then react it with an acid chloride. Now let's look at how we would convert a carboxylic acid into an acid chloride. Okay? Acid chlorides are our most reactive, our least stable carboxylic acid derivatives, so we cannot convert any of the derivatives into an acid chloride. The only way to make an acid chloride is to start with a carboxylic acid. And what we do is we react the carboxylic acid with thionyl chloride. Unfortunately, for some reason, the book forgot a key ingredient, and that is pyridine. We should see pyridine right here below the arrow because pyridine is essential in this reaction. So make sure you include pyridine in your notes. We encountered thionyl chloride back in chapter 7 as a way of converting alcohols into, or maybe it was chapter 9. It was actually chapter 9 where we learned how to convert alcohols into chlorides using thionyl chloride and pyridine. Okay? The good news is the mechanism of converting carboxylic acids into acid chlorides is very, very similar. It only has one step that's slightly different from that mechanism we learned in chapter 9. So let's take a look here on the screen. In chapter 9, we learned that the sulfur atom of thionyl chloride is highly electrophilic. It has 4 bonds to atoms that are more electronegative than sulfur. And so with all of those bonds polarized away from the sulfur, we've got a pretty substantial partial positive charge there. So our weakly nucleophilic OH from the carboxylic acid attacks that sulfur, displacing a chloride. Now, instead of using that chloride as a base in step 2, what are we using? We're using pyridine, exactly. So pyridine is the base in step 2. And those 2 steps have now converted the OH of our carboxylic acid into an excellent leaving group. And we haven't made HCl because we're going to need the chloride in the next step. Right? We've made a pyridinium cation. And in the next step, our chloride, which is a strong nucleophile, is going to attack our carbonyl carbon, giving us a tetrahedral intermediate. Okay? This is the one step that doesn't appear in the conversion of an alcohol to an alkyl chloride because we don't have a carbonyl carbon. Okay? But once we make our tetrahedral intermediate, we can eliminate the best leaving group from that tetrahedral intermediate. Chloride is a very good leaving group, so if we want the chloride to stay on that carbon, we have to have an even better leaving group. And that's what this species is. This is a much better leaving group than chloride. Because when we eliminate it out, it fragments. We cleave that sulfur-chlorine bond. We generate chloride, which is a good leaving group, but we also form SO2, sulfur dioxide, which is a very stable molecule, comparable to carbon dioxide. And it's entropically favored because this leaving group is fragmenting and we're forming more molecules. We're actually forming 3 molecules from one intermediate. This is an entropically favored reaction. Okay? So chloride goes in, chloride comes out, that's neutral. But then when you add in the fragmentation that we've caused, that is entropically favored, then that is why this is a better leaving group than that. Okay? Any questions on how we generate acid chlorides from carboxylic acids? Okay, and provided a good review of the thionyl chloride mechanism from chapter 9, and then also just a reminder that we need pyridine here as the base instead of chloride. Okay. All right. So now let's talk about reactions or how we would form an ester from a carboxylic acid. We've talked about acid chlorides. We reviewed anhydrides. Now let's look at esters. So an ester can be made from a carboxylic acid and an alcohol. So unlike amines, alcohols are not basic enough to deprotonate a carboxylic acid. So we're able to mix alcohols and carboxylic acids and make esters, but we do need a catalyst. Okay? We need an acid catalyst in order for this reaction to occur. Okay? And then water is produced as a result of this reaction. This process has a name. It is known as the Fischer esterification. Emil Fischer was a very prominent organic chemist. I believe he won the very first Nobel Prize, but one of the very early Nobel Prizes, if it wasn't the first, in chemistry. We'll learn about some of his other discoveries later on in the semester. But he discovered this reaction. It is an equilibrium process. Our carboxylic acids and our esters are of comparable stability, so the equilibrium is pretty much a one-to-one mixture. So if we want to drive the reaction to the right, typically we use excess alcohol. Of course, in theory, we could remove the water. In practice, sometimes that doesn't work so well because if we're using a low molecular weight alcohol, it would have a boiling point less than that of water, and you'd end up removing the alcohol instead of removing the water. Okay, so for practical purposes, it's usually easier to use excess alcohol if we're trying to drive this reaction to the right. Okay, so let's draw the mechanism. It's catalytic and acid. So we're going to use the acid, and then we're going to regenerate the acid at the end of the reaction. Okay? So we start off, we protonate our carboxylic acid with our strong acid catalyst. Sulfuric acid is a common one. You could use HCl or other HXs if you wanted. Which oxygen of our carboxylic acid are we going to protonate? The carbonyl or the hydroxyl OH? Think back to chapter 19. Which one do we protonate? We protonate the carbonyl oxygen because that gives us a resonance stabilized cation. We could draw a second equivalent resonance structure, right? Delocalizing that positive charge onto this oxygen. We couldn't do that if we protonated here. Okay, so we protonate. Then we use our alcohol as a nucleophile. That alcohol comes in and attacks our protonated carbonyl. Okay. That gives us a protonated tetrahedral intermediate. We formed the conjugate base of our acid here in step 1. So we can use that conjugate base over here to deprotonate. Okay. So now we have our tetrahedral intermediate. We have our acid. That acid can protonate any of these 3 oxygens on our tetrahedral intermediate. If we protonate the alkoxide oxygen, we're just going to go back where we came from. Okay, so that does happen. But if we protonate one of the 2 OHs, then we're going to go forward in the mechanism. Okay. We're producing that conjugate base again. So by protonating one of the OHs, we've now attached a good leaving group to that tetrahedral intermediate. Water is a good leaving group, and so we can eliminate it. Okay, so we've eliminated water. Okay. Now we have the conjugate acid of our ester, but we produced the conjugate base of our acid 2 steps earlier, so that conjugate base deprotonates, giving us our final product and regenerating our acid. Okay? So if you look at this mechanism, it is a 6-step process. 1, 2, 3, 4, 5, 6. Okay. We have a nucleophilic attack in step 2. We have an elimination of water in step 5. And the other 4 steps are simply proton transfers. Okay. And then to get those proton transfers in the right order and in the right positions, it helps to remember something I mentioned earlier, which is that when we're performing a reaction in acid, our intermediates are typically going to be either neutral or positively charged, with the exception of our conjugate base. Right? Our conjugate base is negatively charged, but everything else is either neutral or positively charged. And we see that pattern. We have a positively charged intermediate here and here, a neutral intermediate here, positively charged intermediates here and here, going back to a neutral. So we're going back and forth between positive and neutral. If you were to generate something negatively charged in base that was not the conjugate base of our acid, then you probably did something wrong or did a step in the wrong order. Okay? Any questions about our Fischer esterification mechanism? Okay, so that allows us to make esters from carboxylic acids and alcohols. The reaction can also be performed in an intramolecular reaction. If we have our carboxylic acid and our ester in the same molecule, okay, we add our sulfuric acid. Here we can't use excess alcohol to drive the reaction to completion because the alcohol is part of the acid. We automatically have a 1-to-1 ratio of those functional groups. But we also don't have to worry about boiling that alcohol off. So if we heat this reaction up, then we're able to drive off the water that is formed. And so that's how an intramolecular Fischer esterification works. Sulfuric acid and heat, driving off the water, giving us a lactone product. Okay? All right. So let's talk about how to make amides from carboxylic acids and amines. I've told you we can't do this directly because we have acid-base chemistry that interferes. But there is a reagent that we can add to a carboxylic acid and an amine that will allow us to form an amide. That reagent is called dicyclohexyl carbodiimide, which is a very long name. The structure of the compound is almost as long as the name. And as we've done in the past with large molecules that have long names, we give it an abbreviation. Okay? So first I'll draw the structure of dicyclohexyl carbodiimide. These are the 2 cyclohexyl groups. This functional group here that looks unusual is referred to as a carbodiimide. So we call this DCC for short. And if we mix it with an amine and a carboxylic acid, we can form an amide. Okay? And then there's going to be a byproduct that is generated. That looks like this. Okay. This functional group is known as a urea. When you have a carbonyl with 2 nitrogens attached, that's called a urea. So this is dicyclohexyl urea. If you look at what's happened here, as we convert our carboxylic acid and our amine into an amide, we've lost the elements of water. We've lost OH from our carboxylic acid. We've lost a proton from our amine. And so this could be viewed as a dehydration process because we're losing a molecule of water. But we're not producing water. If you look at our byproduct, our DCU, and you compare it to the DCC, it has 1 more oxygen and 2 more hydrogens. Okay, so that's where the elements of water end up in that byproduct, the oxygen and these two hydrogens. So let's take a look at the mechanism and see how this process works. We're going to look at this one on the screen, but it's important for you to be able to write it out, so make sure you practice and write it out on your own. I will say that since the cyclohexyl groups are just spectators, there's no need to draw them out every time. Just use R to abbreviate those cyclohexyl groups, okay? So we know that acid-base chemistry occurs when we have a carboxylic acid and an amine or other nitrogen-containing compounds. In this case, we can use that acid-base chemistry to our advantage. If our DCC deprotonates our carboxylic acid, we generate the carboxylate ion, and we have the conjugate acid of DCC. And if we look at just the top half here, this looks an awful lot like an iminium ion. We encountered iminium ions in our last chapter. Iminium ions are electrophilic. And so once we generate this iminium ion, now our carboxylate can attack that carbon. We can push electrons up to the nitrogen. Okay? So in 2 steps, we've taken care of that pesky acidic proton on the carboxylic acid, and we have converted the OH into a good leaving group. As you'll see later, this is the precursor of a good leaving group. Okay? So now that we have our good leaving group attached to our carbonyl carbon, our amine can attack that carbon, okay, generating a tetrahedral intermediate. Okay? Now, step 4, this is interesting. In step 4, we have transferred a proton from the positively charged nitrogen over to this sp2 nitrogen. Okay? It's too bad that the book, I don't know why they left off the curved arrow. Maybe they thought it would look too crazy or something to draw a curved arrow from here all the way over to here. But that's what's happening. We're deprotonating this nitrogen with that nitrogen. Now, hopefully you remember that in previous mechanisms we've looked at, where the book has tried to do intramolecular proton transfers or implied that there was an intramolecular proton transfer, I've said, no, it's an intermolecular process. The intermolecular proton transfer with pyridine or something else as a base is faster than the intermolecular is faster than the intramolecular. But in this case, the intramolecular proton transfer works. Why is that? To answer the question, you need to look at how many atoms there are connecting this proton to that nitrogen. When you know the answer, please raise your hand. It can be either the answer to how many atoms are there or why does this work? I'll take either of those answers. Yes, please. Okay, there's 4 atoms in between. So if you include the nitrogen and the proton, how many atoms would there be in the cyclic transition state? There would be 6, okay? So I've told you before that 4-membered cyclic transition states are strained because 4-membered rings are strained. 6-membered transition states are not strained because 6-membered rings are not strained. So if you can have an intramolecular proton transfer with a 6-membered cyclic transition state, it's going to work and it's going to be really fast. Okay, so you don't have to add base to this reaction to transfer the protons. You can just transfer the proton intramolecularly. Now, the last question is, why are we protonating the sp2 nitrogen and not the sp3 nitrogen? The answer to this question lies back in chapter 8. There were some bases that looked an awful lot like this functional group, and those bases were called DBN and DBU. And when we were talking about DBN and DBU, we asked the question, which nitrogen gets protonated? And the answer was the sp2 nitrogen. Okay? If you remember why, then that explains why we protonate this nitrogen here instead of that one. Does anybody remember that far back? Yes, please, Sydney. Yes, excellent. So when you protonate the sp2 nitrogen, we have a resonance stabilized cation. We have a lone pair adjacent to a pi bond. Anytime you have a lone pair adjacent to a pi bond, you can draw a resonance structure. It's going to be an equivalent resonance structure. So that positive charge is actually shared equally by these two nitrogens. If we protonate the sp3 nitrogen, we don't have the ability to draw a comparable resonance structure. Okay? We've removed the lone pair adjacent to the pi bond. So protonation of the sp2 nitrogen gives us a resonance stabilized species. Okay? All right. Now that we've protonated that nitrogen, this is a very good leaving group. So we reform our carbonyl, we eliminate the leaving group, and that gives us our amide, and that gives us our dicyclohexylurea byproduct. Okay? Questions on how we make amides using DCC? Yes? So if you protonate here, you no longer have a lone pair on the atom adjacent to the pi bond. And plus, this would be the positively charged atom, so there would be no point in pushing electrons towards that atom because it wouldn't be positively charged. Okay, so this works out much better because we have a lone pair on this nitrogen adjacent to the pi bond. We have a positive charge on one of the atoms in the pi bond. So drawing a second resonance structure allows us to delocalize the positive charge. There's no way to delocalize the positive charge if we protonate here. That positive charge is going to be stuck on that nitrogen. Okay? All right, so DCC, if you draw the mechanism, please abbreviate those cyclohexyl groups, just write R. Okay? All right, let's talk now about reactions of esters. Now, esters are less stable than amides. So in principle, you can convert esters into amides. In practice, we never do that, okay? So we learned how to make esters. We can make esters from carboxylic acids. We can make esters from anhydrides or acid chlorides. But we can make amides from all of those species directly. So it would make no sense to convert a carboxylic acid to an ester and then an ester to an amide if we could convert a carboxylic acid directly into an amide. Okay? So because all of the precursors to esters can be converted directly into amides, we rarely convert an ester into an amide. So even though it's possible, it's rarely done, so we're not going to talk about it. So what we are going to talk about instead is how we make carboxylic acids from esters. Okay? And there's two ways to make carboxylic acids from esters. We can, both of them would require water. So these are hydrolysis reactions of our ester. We're going to use either acid or base in this process. The acid can be used catalytically. The base is going to be used stoichiometrically. We're going to generate either a carboxylic acid or its conjugate base, the carboxylate. The carboxylic acid will be the product in acid. The carboxylate will be the product in base. In both cases, we would generate the alcohol also as a product. Okay? So, the reaction in acid is simply the reverse of the Fischer esterification. We've got the Fischer esterification up here on the upper board. We used our equilibrium arrows, so that tells us that if we react an ester with an excess of water in the presence of acid, using that excess of water, we're going to drive the reaction to the left, and we're going to produce the carboxylic acid and the alcohol. Last semester, we learned the principle of microscopic reversibility. We encountered that again in chapter 21. And that principle states that in an equilibrium process, the same intermediates and transition states are encountered in both directions. So the mechanism of the reverse reaction of the Fischer esterification, namely the ester hydrolysis, is simply the opposite of the Fischer esterification itself. So here we see that mechanism up here on the screen, okay? And we use excess water to drive it. So we're going to protonate, carbonyl oxygen, water attacks, deprotonate the positively charged oxygen with our conjugate base, giving us this tetrahedral intermediate. Now you can protonate any of the three oxygens of that tetrahedral intermediate, but protonating the alkoxy oxygen is the one that allows us to go forward, eliminating out our alcohol, and then regenerating our acid in the final step. Okay? This reaction explains why esters are not good perfumes. I told you yesterday that they smell good, but they are not good perfumes. If you put an ester on your skin and you keep it there for a period of hours, what else are you going to have on your skin? Especially if it's a hot day. You're going to have sweat. What does sweat have in it? It has water. What else does it have in it? It has acid, right? Your sweat has got at least some acid in it. So you mix the ester, the water, and the acid, and what do you get? You get a carboxylic acid. How good do carboxylic acids smell? They smell terrible. We didn't get a chance to pass them around in class like we did in most years without COVID. But if you smell a carboxylic acid, you find that one drop of a carboxylic acid can be overpowering. And so that's not what you want to have happen on a long date, to have your perfume or your cologne hydrolyze and turn into a bad-smelling carboxylic acid. So most perfumes and colognes are actually made from alcohols that have good odors to them, as opposed to esters. Okay? So when chemists were trying to figure out this mechanism, when they didn't know which carbon-oxygen bonds were broken in this mechanism, the way they did it was they used labeled reagents. They put O18 labels at certain places and figured out where that O18 label ended up in the products of the reaction. So we're going to ask you the question in reverse. You know the mechanism. Based on your knowledge of the mechanism, if you had an O18 labeled oxygen at this position in the ester, where would that label end up in the product? Go ahead and talk to your neighbors and come up with an answer. Again, this class always talks much quieter than the 10 o'clock class does. Or maybe you're all smarter than them and you know the answers on your own. All right, let's try to get our final answers in the next 10 seconds or so. Okay, 25, good. Keep going. Okay, that looks like everyone for today. All right, where does the 018 label end up? Anybody brave enough to answer? Where does it end up? Yes, the alcohol. Yeah, so the mechanism, it was on the screen. The reverse mechanism is now up here at the top, right? And if you look at that, you see that as we convert the ester into the carboxylic acid and the alcohol, it is this carbon-oxygen bond that is cleaved, not this one. Okay, so because we cleave this carbon-oxygen bond, that labeled oxygen ends up in the alcohol. When chemists were trying to figure out the mechanism, they didn't know which of those carbon-oxygen bonds was cleaved. And so they ran this experiment, they found the label in the alcohol, and that's what allowed them to propose the mechanism that we've taught you today that involves cleavage of this carbon-oxygen bond. Okay? So water is also involved in this reaction. And another question that researchers had was, where does the oxygen atom in the water molecule end up? So we have a follow-up question for you. If we have a labeled water molecule, where does the label end up in the products? Okay, let's get our final answers in. We have a couple more, maybe one more. Okay. All right, that looks like all of our answers. So based on the last question, where we learned that the oxygen in the alcohol comes from the ester, all of you eliminated A. You knew that the oxygen in the water had to end up in the carboxylic acid. But where in the carboxylic acid does it end up? There was a little debate. Okay. It ends up at B. Is that the only place it ends up? Yeah, it ends up at C as well. Okay. So if we go back and we look at the mechanism, we see that our water attacks. After we deprotonate our water, we have two OHs that are equivalent. Okay, so from here, right, actually it's in step 5, where you could draw this curved arrow from either of these two oxygens. And so either of those oxygens can become the carbonyl oxygen, and either can become the hydroxyl oxygen of the carboxylic acid. So because we have these symmetrical intermediates, then that oxygen label ends up getting distributed in two places. Any questions about that? Okay, let's talk now about the base-promoted hydrolysis of esters. This is different from the acid-catalyzed hydrolysis. You'll notice I said base promoted. The base is not a catalyst. It is consumed. So we have to use one equivalent of the base. Another difference here is that the base-promoted reaction is irreversible. It is not an equilibrium, whereas the acid-catalyzed reaction is reversible. Okay? We cannot take base and react base with a carboxylic acid and an alcohol and get an ester. It doesn't work. Okay, so it's an irreversible process. It only goes in one direction, hydrolyzing the ester. Okay, and it has a name. The name is saponification. Saponification means soap making. We'll explain in a couple of minutes how it got that name. Another aspect of this reaction, which is important to note, is that the product is not the carboxylic acid. The product is the carboxylate. If you just add a base such as sodium hydroxide to the ester, you'll get the alcohol, but you do not get the carboxylic acid. You get the carboxylate species. If you want the carboxylic acid, you would have to add some acid, such as HCl, to protonate that. That would have to be a separate step, because you'd want to separate these two components before you did that step, because if you added acid and you had the alcohol present, then you could just make the ester again using Fischer esterification. Okay, so if you wanted the acid, you have to have a separate step of adding a strong acid such as HCl. Okay, so let's look at the mechanism of this reaction and discuss why it is different from the acid catalyzed process. Okay, so we have our ester with carbonyl carbon. We have our hydroxide, both a strong base and a strong nucleophile. There's nothing for it to deprotonate on our ester, so it's going to act as a nucleophile, attacking our carbonyl carbon, giving us a tetrahedral intermediate. Go ahead and draw that. Okay. And I'll draw equilibrium arrows on this step. Okay, this step is reversible, because if we look at this tetrahedral intermediate, we usually eliminate the best leaving group. But here we have essentially a tie. The hydroxide and the alkoxide are going to be basically equivalent in terms of their leaving group ability. If we eliminate out the hydroxide, we simply go back to the start. But if we eliminate out the alkoxide, something different happens. Okay, we eliminate the alkoxide, we generate a carboxylic acid, which has an acidic proton, and an alkoxide, which is a strong base. So what happens next? Yeah, we have an acid-base reaction, a very rapid acid-base reaction. Our strong base deprotonates our carboxylic acid, and that's going to be irreversible. That's going to give us our alcohol and our carboxylate. Of course, the carboxylate forms a salt with whatever cation we used with our base, but since that cation doesn't participate, we didn't draw it. Okay? So this step, again, as I mentioned previously, acid-base steps are favorable if we convert stronger acids into weaker acids or stronger bases into weaker bases. Here we have an alkoxide, that's a strong base. The product is a carboxylate. That carboxylate is a weak base. Resonance stabilized, a weak base. If we look at it from the perspective of the acids, the acid in this reaction is a carboxylic acid, a weak acid. And then the conjugate acid is an alcohol, a much weaker acid, right? pKa of a carboxylic acid is usually between 4 and 5. pKa of an alcohol is usually around 16. So we would have 10 to the 11th or 10 to the 12th for an equilibrium constant for this step. So you can see why we didn't use equilibrium arrows. It is highly favorable and is not going to reverse. So that's why the reaction is stoichiometric in base. We consume base. We start the process with a strong base, hydroxide. we finish the process with a weak base, the carboxylate. So that's not going to be reversible, like converting a strong base into a weak base. Okay? Questions? So as I mentioned, the reaction is called saponification, which means soap making. Back in chapter 3, we learned that carboxylates, or conjugate bases of long-chain fatty acids, make good soaps. We learned that they form spherical particles called micelles with those negatively charged carboxylates on the surface, the long chains on the interior, and that allows nonpolar species such as grease and dirt to get inside those micelles and actually dissolve in water. Right? So that's what happens when you wash your dishes or you wash your clothes in the washing machine, is you form those micelles. So many different civilizations discovered that if they took animal fats have these, you have triacylglycerols, which are esters that have long chain fatty acids, and you mix it with the ash from a wooden fire. The ash from a wooden fire has carbonate, which is not as strong of a base as hydroxide, but a strong enough base for this reaction. So you mix that ash with the carbonate in it, with those triacylglycerols, and you hydrolyze them, generating these carboxylates that function as soaps. Okay, so that's the saponification reaction, probably the oldest chemical reaction in the world, discovered independently by numerous civilizations, because many civilizations were cooking dead animals over a fire, and were, as a result, mixing those triacylglycerols in animal fats with the ash from the wood. And some discovered that they could use that to clean their clothes, clean their cookware, cleaning other things. Okay? Any questions about the saponification reaction? All right, we do have a few minutes left, so we'll briefly introduce reactions of amides, which we'll get into in more detail on Friday. Amides cannot be converted into any of the other carboxylic acid derivatives because they're the most stable. So we can only convert amides into carboxylic acids themselves. And like esters, this is done either in the presence of acid or base. I told you previously that amides provide the backbones of proteins. Proteins consist of amino acids that are linked together by many, many different amides. When you digest proteins, either in your stomach or in the lab, you usually have to heat those proteins up in the presence of acid. Because they're less reactive than esters, usually you have to add heat in order to cleave those amide bonds. Those amide bonds are fairly stable. We need them to be fairly stable because we need our proteins to be robust. But we also need to be able to cleave them when necessary. And so our body has special enzymes that assist in the cleavage of those proteins. When you eat protein, you have enzymes in your stomach. You have acid in your stomach. You don't have a lot of heat, but you have acid in your stomach plus those enzymes that allow you to cleave those amide bonds. Let's first look at how acid promotes amide hydrolysis. And the mechanism is going to be almost the same as amide-promoted ester hydrolysis. So we're going to look at this mechanism here and just imagine that we have NHR here instead of OR. It's going to start out the same. Water attacks, we protonate the oxygen, water attacks. We deprotonate this oxygen. So we have this tetrahedral intermediate, but we have a nitrogen here instead of an oxygen. And when we protonate that tetrahedral intermediate, the nitrogen is going to be more basic than either of the oxygens. So it makes sense that we're going to protonate the nitrogen. Okay, so we would have this species, and we would have a nitrogen here instead of an oxygen. So then we would eliminate out an amine. So far, everything's the same, except we just have a nitrogen instead of an oxygen. But here's where it gets different. Okay? So when we eliminate out that nitrogen, we're going to have the conjugate acid of our carboxylic acid. We're going to have our amine, and then we're going to have our conjugate base. Okay? So when we're hydrolyzing esters, we use the conjugate base of our acid to deprotonate the oxygen. What's going to be more basic, the amine or the conjugate base? The answer is the amine is going to be more basic. So when we're hydrolyzing an amide, it's the amine that deprotonates the carboxylic acid. Okay? So we get a carboxylic acid, but instead of regenerating our acid, what we have done is we have formed an ammonium salt. Okay? So our conjugate base forms a salt with this ammonium ion. What this means is the acid-promoted hydrolysis of an amide is stoichiometric in the acid because we've consumed the acid. Because of the increased basicity of the amine compared to the alcohol in the ester hydrolysis, this amine deprotonates the carboxylic acid, conjugate acid, and we generate this ammonium ion. Okay? So hydrolyzing amines in acid produces ammonium ions. And as a result, it is stoichiometric in the acid and not catalytic. Any questions? All right, we'll stop there. We'll talk about base-promoted amide hydrolysis and continue on and finish the chapter on Friday. Hope to see you on Zoom on Thursday evening and try to watch our review session online before then.